All right, everybody. Hello and welcome to our review of types of analysis. All right, so this is our, as promised, statistical overview in this class. So this is not a statistics class per se. All right, but you will be using statistical tests to conduct your own research. So this is a conceptual overview about the different types of analysis, which hinge on things like different types of data and variables that we've been discussing in class so far. So I start us off here with a decision tree, which I think is helpful. So let me move my head. So here we have a decision tree to help you determine what type of statistical test to use. This might seem a little bit convoluted, but hopefully you can sort of trickle down here and think about your variables for your hypothesis. All right, so remember we have 4 different types of data. All right, we have nominal, ordinal, interval, and ratio data. That will be indicated here. If you look up top, that's our first distinction. Do you have interval or ratio data, or do you have a nominal scale? All right, so if you sort of follow the line down here, you think of how many, say, predicting groups you have, what type of data you have as your outcome versus your predictor. And we basically fall onto a few tests that we will use for this class. And I will help you determine which you need to use for your hypothesis. And many hypotheses can be tested using a combination or multitude of these tests. But these are the main ones we will talk about. We will talk about t-tests. We'll talk about ANOVAs, we'll talk about correlations, and we'll talk about chi-squared tests. There are, of course, others, but these are the most flexible and will address most of our hypotheses here. So hopefully this helps you to sort of sort through some of the elements of decision making in this process. And now we're going to talk about hypothesis testing, recapping hypothesis testing. So hypothesis testing is the bread and butter of statistics, all right? So if you've already taken statistics, you hopefully know this. But if you're taking it currently, this might be a sort of new topic to you. So we're going to try and recap it or talk about it in a pretty simple way here. All right, we have 2 hypotheses, all right? Whenever we come up with a research idea, we generally come up with a hypothesis. That would be the alternative hypothesis. That's your prediction. And you're going to pit your prediction against something else. And what we normally do is compare it to the opposite of your prediction. If you're predicting a difference between 2 groups, maybe that males and females spend their leisure time differently, the null hypothesis would be that males and females do not spend their leisure time differently. All right, it's the exact opposite. And in fact, it's a mathematical opposite. And that's kind of what we want to talk about here today. When you run a hypothesis test, when you run a significance test, only one of 2 things can be true. And we base it around the null hypothesis. We can either retain the null hypothesis and say that our alternative hypothesis was not supported, we need to go on believing the null hypothesis, or we can reject the null hypothesis and we can say that we have some evidence to suggest that our alternative hypothesis is true. And how do we do this? We do this using probability. All right, hypothesis testing leans on probability, and we're going to be using mostly, in this class anyway, a p-value of 0.05. This is sort of our gold standard in science. It's inherently flawed, and we'll talk about that later in the class. But this is what we use. We call 0.05 or 5% unlikely to happen, right? If there's a 5% chance of something happening, we say that that's generally unlikely to happen. So if we find a p-value that is less than 0.05, then we found a significant difference, something that happened that seemed unlikely to happen if the null hypothesis was true. All right, so I like to take another example of this as well. Let's think about flipping a coin, all right? We know that when we flip a coin, we have a 50% chance of getting heads or tails, right? That's a basic probability. But what's the probability that we get, say, 10 heads in a row? All right, that's not very likely. In fact, if we flipped a coin 10 times and got heads every time, we almost might become suspicious that the coin is maybe weighted or not working as a normal coin. So here's a sort of overview of this, all right? So P is a probability, and we want to conclude that our findings are not happening, or we're not detecting a difference in scores or groups or whatever we're measuring just due to chance. All right, so let's set this idea up as an actual hypothesis test. All right, so the null hypothesis would be, all right, what we go in believing in this case would be if we have a coin, we'll say, okay, this is a fair coin. But our prediction might be that it's weighted, right? Maybe you've flipped it many times and you've said, hey, something's up with this, right? This isn't working out quite as it should. So the question is, how much convincing would it take for you to believe that coin is weighted? So you might have a gut feeling about this yourself, but in science, that's what we use P equals 0.05 for. If we find something that was less than 5% likely to happen, if the null hypothesis were true, that's when we say maybe the null hypothesis isn't true anymore. Maybe we have some evidence to suggest that it isn't true. So if we take a look at this, okay, this is basic probability. Basic probability is such that our number of successful outcomes are divided by all possible outcomes. So if we take flipping a single coin, I have the example with tails here. If we flip a single coin and we want to predict how likely we are to get tails, tails is 1 out of our 2 possible outcomes, so that would be 50%. All right, if we get 2 in a row, we have to multiply those probabilities together. If we get 3 in a row, we have to multiply all 3 of those probabilities together, and so on. So if you take a look at just the probabilities here, once we get to about 4 tails, excuse my, oh, you didn't see that. All right, once we get to 4 tails, we're at a 6.25% chance of that happening. Remember that probability is just that, it's just the chance of something happening. People still win the lottery with a 0.00001% chance. So it could be that this series of tails is happening and the coin is not weighted, and it's just that we've come across a string of unlikely occurrences. But if this continues, right, if we go up to 5 tails, 6 tails, 7 tails, that succession becomes less and less likely to happen due to chance, and that succession might be happening due to something else. So this is a general idea that underlines all of our different types of statistical tests that we can use different types of data for. But if we have a null hypothesis, all right, and we test our hypothesis and we find a significant difference, then we can say that our prediction seems to be supported and the null hypothesis does not. So if we hop back to the hypotheses here, right, if we get a probability that is less than 0.05, that would be support for our H1, or our alternative hypothesis, or our prediction against the null. All right, so jumping ahead here, let's talk about our first type of test, first type of statistical test that you might use in your analysis. And most importantly here, we want to think about what types of data would go into an analysis like this. So let's first discuss why run a t-test, all right? When and why would we run this type of test? Well, a t-test compares means across groups. So we compare nominal groups, and we compare interval or ratio variables between those two groups. All right, so the question is, how convinced do we need to be that there's a true difference between the means? So much like our coin flipping analogy, we basically need evidence of enough divergence between the two groups that we're comparing. So if you take a look at this image up here on the top right of the slide, it might be such that the two means that you're measuring, that you're looking at, might be pretty close to each other on a normal distribution, but it might be that they're so far apart in B here that they belong to separate distributions. I often kind of hop back to male and female differences because I think it's a great way to think about this. We talk about things like anxiety and depression being more prevalent in females, but things like ADHD and autism being more prevalent in males, right? We do see these psychological differences between the genders. So if we think about it this way, we're basically asking, can these groups live together? Is there no difference between the groups as the null would suggest? Or, alternatively, are they so different, right? Are they significantly statistically different that we need to treat them separately? So that's what a t-test does. It takes two groups, compares means between those groups to see if the groups are comparable or not, if they come from the same distribution or not. And this is also going to be based on those p-values. There has to be a less than 5% chance that the difference between the groups occurred due to chance. So again, we use this to look at two independent groups for the independent variable, nominal variables, categories, with one dependent variable, an outcome variable. So if we take a look here, all right, for example, we could compare the mean number of days that smokers and non-smokers exercised in a month. All right, and we could take a look at those two groups, see if there's a difference. We can make a bar graph like we've practiced in class. We can look at that difference visually, but we could also run a hypothesis test to see if there's a statistically significant difference, if this difference was unlikely to occur due to chance. All right, now let's talk about ANOVAs. And ANOVAs are very similar to t-tests in that they require a nominal independent variable and a ratio or interval dependent variable. But what ANOVA can do that a t-test cannot do is compare more than two groups. An ANOVA can compare 3 or more groups, 3, 4, 5, 6, 7 groups. We usually cap ANOVAs off around that point. But we can take a look at multiple groups compared to each other. So an example I think that is great here is maybe comparing, let's say, let's go back to leisure satisfaction. We could ask people who are unemployed, employed part-time, and employed full-time, how satisfied are you with your leisure time? Right, we might expect differences across those three groups. So here's a graph here. This is called box and whisker plotting. We would likely do something more just like a bar graph with error bars being those little T-looking shapes on the top and bottom of these boxes. But it compares three groups, and those black lines that you see inside of those boxes are the means for each group. So we're comparing the mean, the spread around the mean, and then the error in the data. And again, if you're new to statistics, currently taking it, haven't taken it in a while, or trying to remember what they even are, one thing that we really need to remember about statistics is that there's error in them. We're relying on things like probability and sampling that are imperfect. So even if we have a sample and we detect a significant difference, in order to really believe in that significant difference, we would need to replicate that finding again and again and again, until we can basically kick that null hypothesis out and say, hey, that doesn't seem to be true at all. In fact, our new null hypothesis should be what we've continued to find support for through the research. A little bit of an offshoot there, but still important. All right. And what are we looking at in an ANOVA? Well, this is true of t-tests as well, but we're looking at variance. We're looking at how much variation there are in these groups as well. It's not simply a means comparison, because we're also interested in how much do the groups vary within themselves, right? How much leisure satisfaction varies in those who are unemployed versus how much do they vary compared to people who are employed part-time and employed full-time, right? So we're looking at variance in all sorts of different ways, all right, which is why I think this outdated meme is applicable, because we're talking about variation within groups, between groups. Sum of squares is how we find variance. So that's really what we're looking at here. We're looking at spread. And that's what this graph helps to illustrate as well. The length of these boxes expresses that variance around a mean. All right, so what do we conclude? And I just love this image because it is so cute. But we basically determine if any of the groups are different from each other, right? Are any of these groups sort of independent of each other? We can have groups that even have the same means but have such dramatically different spreads that they might be statistically significant in terms of their differences from each other. So some of you might be taking a look at this yourself. Maybe you want to compare people who do not consume alcohol to people who consume it socially to people who consume it often or daily, right? That's a comparison of 3 groups. Maybe you want to include groups of people who are not involved in any extracurricular activities, people who are involved in maybe 1 or 2, and people who are involved in multiple extracurricular activities to maybe look at things like academic success or social satisfaction. So the ANOVA is a very flexible test, and many of us will be using it in here if we're interested in comparing multiple groups. All right, a sort of different direction now is in the correlation. So correlation, I love to talk about correlation because I think correlation is one of the most chronically misused words in all of statistics, all right? And you're going to be all the wiser now and understand what a correlation really is. A correlation compares 2 interval or ratio variables. So if you ever hear anybody starting a sentence, right, by saying, comparing groups, saying these 2 groups are correlated, there's no such thing, right? No such thing. That's not right because we can't correlate groups. We can only correlate variables that are continuous. Well, let's move my head instead of the slides. All right. So we ask if 2 variables are related, all right? Correlation means co-relationship right there in the word. We want to know if 2 variables are related. Does one rise as the other falls, all right? As we maybe spend more time watching Netflix, we maybe spend less time studying, all right? Maybe as we spend more time exercising, we gain more self-confidence. All right, so we're looking at variables that move together, things like time, things like scores on different measures, right? Not comparing groups. We need 2 continuous or ratio variables to run a correlation. All right, so again, co-relationship, that's how we should think about it. We're not looking at group differences. We're looking at how 2 things relate to each other. Are they related at all? And we can get correlations that range from a number of values. We use a correlation coefficient that measures from -1 to +1. And we'll take a look at that next after you take a look at this, another very funny comic. If you're a stats nerd. But about an issue that happens all of the time, right? People will attribute correlations to 2 variables where the actual thing that's correlating with both of those variables is time, is that things change over time. All right, so we have cancer incidence rising and cell phone usage rising. And then we see a funny conclusion here that, that cell phones cause cancer, right? Or cancer causes cell phones. But in reality, we can't make any claim like that because correlation does not imply causation, which might be another little term you've heard before. But it just tells us if 2 variables are related and how related they are. If they're very strongly related, if we have a very high correlation coefficient, closer to +1, if we have something closer to 0, that means there's no relationship present, or a negative correlation, right? As one thing rises, the other falls. Again, think more time on Netflix, less time studying, right? And correlations are nice because they're easy to visualize. These are all great to visualize, right? We can visualize, say, a t-test, compare 2 means and see how different they really are on our scale. Here we can see the trend of the data, right? Is there an upward trend, a downward trend, no trend at all that you can discern? And of course, we use hypothesis testing here as well. So just a few examples I like to talk about. Video games, all right? Do we think video games are evil? I feel like there's a lot of research that really, with video games specifically, it's like, video games are great for problem solving, but then wait, no, video games are terrible because of violence. So it naturally falls somewhere in between But it's certainly an interesting topic, especially with the intense rise in the past decade or so in availability of video games. But I digress. This is a correlation between video games and alcohol consumption, which was a study I stumbled upon some time ago that I thought was fairly interesting. I also thought that gamers might have a different drug of choice than alcohol, if you know what I mean. But anyway, here we have a relationship. And this is showing a positive relationship, that as hours of video games per week increase, as does number of alcoholic drinks per week. All right, so these things rise together. This would be a positive correlation just by looking at it, right? It kind of has an upward trend. And then here's another video games and test scores. All right, average hours of video games per week with exam scores. This is a more kind of slight negative trend. Right, we have exam scores on the y-axis, hours of video games on the x-axis. So as video game hours increase, exam scores decrease. So remember that correlations are comparing two scores for one person. All right, so if you look at any one dot on this graph, we're looking at one person's hours per week of video games and one person's exam score measure. So do we have outliers or sort of abnormal scores in here? Sure, right? We have somebody here that has 15 hours of video games on average per week, but still has a relatively high average exam score. Doesn't mean that it can't happen. It just means that we're looking for general trends across people, which is why we have to say that correlation does not imply causation, right? We can't say that video games are causing the decrease in exam scores, but we can just say there's a relationship between the two. And then just another comic for your fancy. All right, there's lots of comics about correlation, again, because it's so misused. And I hope that what you learn in this class will help you better interpret the word correlation out in the world, and you can notice when people are using it incorrectly, because correlations are very limited in scope. All right, then we have the chi-squared test, not the chi-square, the chi-square. Chi-squared looks at frequencies. All right, so we look at nominal data and how frequently we have scores occurring in our different categories. All right, so a chi-squared test looks at frequency. Let's take a look here. All right. It looks at frequencies of observed and expected values. So again, if you've taken statistics, you might remember the formula. I'm sure it's very important to you when you commit it to memory, but it uses observed and expected values to indicate if we have something abnormal. Remember, normality is kind of what we're looking at here. And we want to know if the distribution of the frequencies across our groups, our nominal categories, is due to chance or not, or if there's an actual trend in the frequencies falling into each of these groups. So observed values are what we actually find in the study, the data that we collect. And the expected frequencies are what we would expect proportionally if the null hypothesis were true, or if there was really no difference between what you were observing. So let's take a little look at an example here. We could compare across gender, all right, a categorical variable, if there's a preferred medium for learning information, all right? So we could have some different groups here, comparing books and online across the groups. And just frequency, right? How many males reported that they prefer books? How many males reported that they prefer online, right? And same for female here. All right, so now what I'm going to do is I'm going to hop over to the whiteboard, and I'm just going to draw out a few things, because this is what helps me when I'm thinking about how we might want to handle a specific data set. So let's kind of go through each of these tests here. Let's start with the t-test. All right, the t-test. All right, so a t-test compares two groups, okay? Compares two groups. All right, and by groups, we mean nominal categorical data So this would be our independent variable. We're comparing two groups, okay? So this would be our predicting variable. And then we'd have an outcome variable. We would have a continuous outcome. My goodness. We'd have a continuous outcome variable or a continuous dependent variable. So let's think here what we want to do. Let's say, all right, let's get a graph going here. Let's say we want to compare two groups. Let's say we want to compare pet owners to non-pet owners. All right, and we want to compare them on, of course, happiness. All right, then we would compare means, right? We would get two means, and we can only get a mean if we have a continuous outcome variable. Remember, by continuous here, what we mean is interval or ratio. All right, so let's say we compare these two groups. Let's say happiness. All right, let's say we're just measuring average from 0 to 10. All right, so let's say that we got pet owners up here, non-pet owners down here, okay? These are our mean differences, right? We can compare the means. Maybe the mean here is a happiness of 7.8, maybe here it's 3.4. You would run a t-test, all right? You wouldn't just take a look at this and decide. You would run a t-test. You would run a hypothesis test, and you would see how unlikely this difference in means was to occur by chance. Was this just due to your sampling, or does there seem to really be a difference between pet owners and non-pet owners? So that's what you would do. You would run a test. You would look to see if your score was unlikely to happen, right? If you get a t-value all the way over here. And remember, you might have done this by hand in your stats class, but we're going to have SPSS do this for us in this class. So if you're panicking, like, I don't know how to determine that by hand, what SPSS is going to do is it's going to spit you out a p-value, and if it's less than 0.05, then there is a significant difference between your groups. So we'll get to all of that in greater depth when we get to our lab on t-tests, but that's the general idea here. All right, so let's try ANOVAs now. All right, what do you need for an ANOVA? Well, you need, you're going to compare, all right, 3 or more groups. All right, so remember, this will also be nominal or categorical. And this would be your predictor, your independent variable. And then you're going to have a continuous outcome variable. All right, and let's say this is going to be interval or ratio. You also might be thinking, where is ordinal data in all of this? Well, ordinal data is a little tricky because it depends on the how many rank orders we have. It might be that you want to turn those rank order scores into groups, or sometimes we're a little sneaky and we treat it sort of like an interval variable. So it sort of bridges the gap for us. We can use interval variables in correlations using a special type of correlation called a Spearman-Rho. But again, I'm ahead of myself. We're on ANOVAs right now, so let's talk about that. All right, so in ANOVA, all right, much like a t-test, all right, we would have a graph. We would have 3 or more groups, all right? Let's see, what do we want to compare here? We don't want to keep my same old. Let's go for different housing situations. So let's say people living with parents or with family, with parents, with roommates, with spouse, okay? And then maybe we have like another, maybe like with parents, or we have with family for people living with siblings or grandparents or aunts and uncles, right? Other family structures here. Let's start with just these 3. And let's say we just want to look at their life satisfaction, all right? This might be a sensitive topic right now in our 2020 world, but let's roll with it. All right, so life satisfaction, let's keep it simple again and say we're looking at it on a 0 to 10 scale. So let's say for those living with parents, 5, with roommates, here, spouse, here. All right, then we would compare these groups. And remember those little t's I was talking about? There's going to be some rate of error here. All right, so even if you see group differences like this, so notice that this is higher than this. But when we include the error bar, all right, the error bar kind of suggests, hey, maybe in a different sample, this group would be higher than this other group. And of course, these kind of go both ways here. But this is the idea with an ANOVA. We're comparing three groups on some type of continuous measure. Let's get another slide. Let's do correlation next, all right? So for correlation, we're comparing two continuous variables, all right? And they need to be interval or ratio. All right, so if we draw this out, let's say that we want to look at the relationship between dates gone on per month, all right, dates. How many dates are you going on, all right, per month? I don't know, what do we think the high end of dates per month is? A little tricky. Let's go from one, well, tragically, I guess we'll start at 0. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, maybe there's more than 10. Maybe someone's dating every day, but we'll leave it here for now. And let's say we want to see how this compares to social satisfaction. All right, and we'll do the same kind of idea here. All right, so the idea would be we'd take one person, all right? We would take one individual and we'd ask them, all right, how many dates do you go on? That's our X variable. And then how satisfied are you with your social life? All right, so maybe one person says, okay, I go on 4 dates a month, all right, maybe 1 a week, and I'd say I'm at a 7 with my social satisfaction. So we'd go to 4 dates here, a 7 for social satisfaction, and we'd kind of plot them right here. And maybe we would just go down the list, right, and keep doing this until we have a sort of trend in the data coming together, right? The more data you have here, the better the trend will sort of start to appear to you. But maybe you start to notice a positive trend, right? We would call this a positive correlation, and we would, of course, test this. We test all of these using comparing all of our data to the normal curve, to our null hypothesis, to see how likely a relationship like this was to occur just due to chance. All right, that's correlation. Let's just talk about chi-square, the last of our major tests here. So a chi-square compares frequencies. So frequencies are different than scores. Frequencies are sort of like tallies of how many people select a certain option. So it compares frequencies, so we're comparing categorical. We're comparing categories or nominal data. All right, so let's go ahead and draw this out as well. Let's say we want to do a chi-square. Let's say we want to do something like, what do we want to do? Let's say we want to compare males and females, and we want to know if they get social support from their partner, all right, or from their friends. All right, so let's keep it really simple. So we're going to ask males and females, do you get social support from your, we'll do a couple different colors here, from your friends. Let's say the blue bar is friends, okay, so, and then over here, of course, would be frequency. So males, let's say they get more support from their friends than from their partners. And let's say females are the opposite, more support from their partners than from their friends. All right, so this would just be frequency, right? Maybe you have, you would be looking at pretty much percentage of your sample of each person that selected these. So let's say you have maybe upwards of, let's say this is around like the 50 mark. All right, so about 50 people selected this, 60 here. Let's say you asked 100 people, or no, I guess that won't work. Let's say we asked 70 people total. So we'd have something like 10 here, 20 here, right? So it's kind of comparing the distribution of choice here of these different categorical variables. All right, so I hope that this has been helpful in reminding us of the different types of statistics that are out there and what we can use for our projects. Remember not to get too bogged down in sort of how to run these tests, but think more about conceptually what they look to address about a research question. So when you think about the variables that you're going to want to use for your study, think about where does it fall in terms of these different types of tests. Am I using categories? Am I using continuous variables? And sort of think about the different ways that you can get to an answer for your hypothesis. All right, well, that wraps up our statistics review. Of course, be in touch if you have any questions on this material.